Hello everyone. So we already have started physics associated with sensors. We started the capacitive sensor, and we have seen what is a capacitor and how we can use a capacitor as a sensor. So in capacitor discussion, the basics associated with capacitor was discussed. Then we also have seen if you have a capacitor, then you have to engineer this structure in order to use this capacitor for any sensing application. So in this lecture we will see what are the capacitive sensor architecture, how we can use this capacitor as a sensor, and what type of geometries will help us in converting a simple capacitor into a sensor. So here I have shown two very widely used capacitor structures or capacitor architecture or geometry that can be directly used for sensing application. So the first one shown over here is again a parallel plate capacitor, where you have a say metal electrode in the top and bottom. Then you have connected these two metal electrodes with a voltage source. So these metal electrodes are connected to a voltage source. So to represent this, we have connected the top electrode with plus V volt, and the bottom electrode is grounded. Now say you have a kind of application where you can actually move this dielectric in between these two metal electrodes in and out. What I mean by that is, this dielectric material is movable. Now from this structure it is very clear, if you take this dielectric out, then the dielectric constant will change partially inside this capacitor. So a section of this capacitor will have a dielectric constant, say epsilon 1, and say this material has a dielectric constant epsilon 2. And based on this position of this dielectric material, for example, now it is positioned like this, based on its position you will be able to figure out the total capacitance associated with this capacitor. So if someone measures the total capacitance, then definitely you will be able to measure the position of the dielectric material that is movable. Secondly, you can also use this parallel plate capacitor in a situation where you will find that this dielectric inside the material is actually changing either upward or downward direction. This may be a situation where the dielectric inside this parallel plate capacitor is reacting with some material and slowly converting to a different material, and this material the conversion depends on the reaction that is taking place. So in such a situation also you will have two dielectrics. Effectively it will have two dielectrics, one is epsilon 1, another one is epsilon 2. Now based on the total capacitance, because if you change the dielectric inside the material, inside the parallel plate capacitor, then definitely your total capacitance will change, and based on the total capacitance value you will be able to understand what is the say width of this dielectric material. So we will see how to calculate that, but let us discuss these two basic geometries that are associated with capacitive sensor. So in this case, for the first structure, let us consider that the parallel plate capacitor has two dielectric materials. One is epsilon, one has an dielectric constant epsilon 1, another has a dielectric constant epsilon 2, and at a certain distance when you are say taking out this dielectric material, then the area under this material or the cross sectional area covered by this material is A2 and the rest is A1. So obviously the total cross sectional area of the parallel plate capacitor is A1 plus A2, right? And then the distance between the electrodes is D, right? Now in such a situation, if you try to simplify this capacitor structure, you can assume that this is a combination of two different capacitors. In the left side you have a capacitor, say C1, in the right side you have a different capacitor, that is C2. Now C1 capacitor has a dielectric material epsilon 1 and a cross sectional area A1. However, the distance between the electrode is D. In case of C2, you have a dielectric material having dielectric constant epsilon 2, cross sectional area A2, and in this case also the distance between the electrodes is D. Now the value of C1 can be given as epsilon 1 A1 by D. So epsilon 1 can be say epsilon 0 into epsilon R1. Okay. So epsilon 1 A1 by D, we have seen the equation in our previous capacitor discussion, and in case of C2 the equation will be epsilon 2 A2 divided by D. So now you have both the values C1 and C2, and if you look at the capacitor structure, or if you try to find the equivalent capacitance of both these capacitors, it is nothing but two capacitors connected in parallel. That is, the equivalent capacitance or total capacitance will be C1 plus C2. That is, two capacitors are connected in parallel, right? So the equivalent capacitance or total capacitance is equal to C1 plus C2. So you can very easily calculate that CT is equal to epsilon 1 A1 by D plus epsilon 2 A2 divided by D, or if you take 1 by D in common, it's like epsilon 1 A1 plus epsilon 2 A2. Now once you move this dielectric material either out or in, the value of C1 and C2 will change, hence the value of CT will change. Now based on this CT value, one can understand what is the position of the dielectric material here. Now this type of capacitor or this type of capacitive architecture or geometry can be used in various situations. So we will see in what are the different situations where you can use that, but to give you an example, for example, say if you have say if you want to measure the distance or the separation between two different electrodes. For example, say you have a machine where one part of the machine is connected to this side and another part of the machine is movable, which is connected to the dielectric material. I am just giving you an example. And then it is very important to measure the distance between these two parts of the machine. In that case, you can introduce a capacitive sensor of this sort and say this distance is in 1 mm or in the order of mm, say tens of mm, or maybe less than 5 mm or so. So in that case, what you can do is you can use a similar structure of this sort. You connect a dielectric material with one end of this other movable part of that machine, and then if this machine comes closer to this fixed part, then the capacitance will change, and from that you will get to know what is the distance. So this could be one application, but the similar architecture can also be used for several other applications. I just have given you one possible application, and then in this case you will be able to figure out the distance. So, this particular capacitor can be can work as a distance monitor to monitor the distance between say different parts of a machine. Okay. Similarly, in the second case you have two metal electrodes, and then you have connected these metal electrodes with say a voltage source, and then say this dielectric material is actually movable in this direction. Let us consider at a certain instant this distance is d1 and this distance is d2. So, the electric field in both these materials will be different because dielectric constant is different, and hence if you simplify this structure you may find that this is nothing but two capacitors C1 and C2 connected in series. So, two capacitors are connected in series. So, in this case your total capacitance will be 1 by Ct is equal to 1 by C1 plus 1 by C2. So, this is what is your total capacitance. So, 1 by Ct is equal to 1 by C1 plus 1 by C2. So, this is your total capacitance value. Now, in this case also you can very easily calculate the value of C1 and the value of C2 the way we have calculated in the previous case. Put those values over here and then you will be able to get the total capacitance associated with that. So, this is the reciprocal of total capacitance. Now, just by measuring the total capacitance or of this parallel plate capacitor, you will be able to understand what is the value of D2. So, one possible application could be, for example, say you have taken an material, dielectric material, which is reactive to a chemical, say A. Now, if the concentration of A is high in the nearby place, it will react with this material and say the reaction will start from the bottom side towards the top side. So, if this type of arrangement you can make, in that case this parallel plate capacitor can work as a say chemical sensor. This may also happen that the reaction will say create a structure like this. So, if you are exposing the chemical from this side, say this part will be reacted first and then slowly it will reduce. So, in that case you have a capacitor which has a dielectric material epsilon 1 in this side, epsilon 2 in this side, then you have two parallel plate in these two sides. This also can be solved. You can also solve the total capacitance value for this. It is not very difficult. I leave it to you to figure out how to solve this type of structure, and you will find in various books as well. It is not very difficult. In that case, what you have to do is you have to take a say very small cross section, and then you should start your calculation, and then you can integrate this from say 0 to L. If the length is L, say from 0 to L, you have to integrate the expression, and then you will get the total capacitance value. So, if you try this in your home, you will be able to figure it out. It is not very difficult. Now, this is what I have shown here. These two architectures are kind of a parallel plate capacitor which can act as a sensor. Now, similarly, you will find not only the parallel plate capacitor that you make or any capacitor structure that you make will act as a sensor. In certain cases, you may make a sensor where you do not need any capacitor, maybe a resistive sensor, but the arrangement of the sensor is such that it will give you a certain sort of capacitive effect. One of the example of this type of capacitor is, say, a interdigitated electrode. Interdigitated electrodes are, say, parallel electrodes connected to each other. For example, it's like, comb like structure that are coming close to each other. So both of them are coming close to each other. In this case, in case of resistive sensor, you will find interdigitated electrodes are very popular, because once you put material on top of this interdigitated electrode, you will be able to get a higher kind of surface area covered using these electrodes. So this provides a better response. Okay, but one of the problem with this type of interdigitated electrode is, this electrode and this electrode both acts as a parallel plate capacitor, because both are conductor, and then you have a dielectric material, say the substrate or the air in between will act as an dielectric material. So you will get a capacitor C1 in this case. There will be a capacitive effect, and this capacitive effect may hamper the sensor performance. So it's not only the capacitive sensors. Sometimes you may get certain sort of capacitive effect in your circuits and some other sensor which you need to consider when you are developing the system. So in this case, you will find there is a capacitance C1 between electrode 1 and electrode 2. Then again between 2 and 3 you have C2. Then between 3 and 4 you will have C3. Between 4 and 5 you will have C4. Between 5 and 6 you will have C5. Then between 6 and 7 you will have C6, and finally between 7 and 8 you will have C7. So there are 7 different capacitors in this interdigitated structure, and each of these capacitors are kind of connected in parallel to each other, right? So if you take the total capacitance associated with this, it's nothing but C1 plus C2 plus C3, so on and so forth. Say if there are n number of electrodes, then it will be total Cn. If there are n number of electrodes, it's actually will be n minus 1. For 8 electrodes, the number of capacitor is 7. So for n number of electrodes, it will be Cn minus 1, right? So if you take the total capacitance, it's n minus 1 into epsilon 0 epsilon r A by d, because in all the cases, let us consider the distance between two electrodes are same, and also the length of all these electrodes are same. If this is the case, all C1, C2, C3, C4 values are equal. So you have n minus 1 number of C. So in total it will be n minus 1 into C, and the value of C is epsilon 0 epsilon r A divided by d. So this is the total number of capacitance you will get. So total number of capacitance meaning the total capacitance associated with this n minus 1 capacitors. Sometimes it may happen that when you are making this interdigitated structure, maybe the one of the electrodes are broken in one side. So this electrode then will act as a capacitance, say C1 and C2, which is not connected in series, not connected in parallel, rather connected in series, if it is broken in one side. So in that case, you have to take that into consideration. So these are the different consideration associated with various sensors where you may find an capacitive effect. Similarly, say you make a PCB circuit, you will find in case of printed circuit boards, different these lines associated with the connection or interconnects are actually parallel to each other and very close by. In that case, these two track will create a capacitance, and this capacitance may affect, say if there is any other capacitor present, or this capacitance will add to this capacitor which is connected to the circuit. This may come in series or may come in parallel, but this type of capacitance sometimes may create some issues. So one has to be very careful when they are making these printed circuit boards, or when they are making some sensors which may have similar type of capacitive arrangements. So, these are the considerations that one should take care. So, there are 3 take home messages in this lecture as well. So, the first one is various capacitor geometries are possible. We have seen that you will find a capacitor geometry where maybe the dielectric material is kind of movable. So, you will find if this dielectric material deflects from its original position, then the total capacitance value will be able to give you the position of this dielectric material. This can be an indicator of various different things. Then the second thing is electrodes may also create capacitive effect. We have seen in case of interdigitated electrodes, this comb like structures, which is very common in case of resistive sensors. You will find these type of structures very commonly in resistive arrangements. So, they may create capacitive effect. So, one has to be very careful when they make similar structures for a sensing application, especially when they connect this with a system. And the third thing is multilayer dielectric may create series and parallel equivalent capacitor, that we have already seen. For example, in this case also it is like multilayer dielectric. The dielectric here probably is epsilon 1, here it is epsilon 2. So, you will find either series or parallel combination of this multilayer dielectric. Say if it is the epsilon 1, if it is epsilon 2, and then you have parallel plates there, then again it will create either series or parallel capacitor effectively. So, these are the different things that one may consider. So, in the upcoming discussion, we will see some of the application of this type of capacitive architecture, so that it is very clear to you how we can use those sensors or those capacitors for various different application. We also will see what are the different or major types of capacitive sensors based on the geometries or arrangements. So, till then, thank you.